G'day YouTube. Welcome to my video series on Mathematics Essentials. In this video series I'm going to cover basically topics that you are going to want to have a handle on in your first year of university mathematics. Okay, I considered calling this video series Mathematical Foundations, but I didn't want to suggest that I was going to be exploring topics that are also associated with the foundations of mathematics, and by that I have in mind topics like axiomatics, set theory, piano, arithmetic, mathematical logic, model theory, those kind of things. Okay, that's the topic of another video series. Okay, so this video is really just to let you know what topics I'll be covering in the video series. So I'll start off with some revision and background knowledge, and basically these are the things after which you'll be able to tackle everything in the rest of the video series, I think. So that's going to include set notation, real numbers and interval notation. We'll talk about absolute value. So I will talk about the graphical or the geometric and the algebraic interpretation of absolute value, because I think it's often confusing when people see it for the first time. And then I'll talk about sigma and summation notation, surds. We'll do a review of trigonometry, and then we'll do some more trigonometry. The index and exponent laws. Index or indices are just another name for exponents, and perhaps I'll prove all of them for you as well, and then we'll do a review of logarithms. After that, we'll move on to non-revisionary content. We'll start doing new stuff. So we'll talk about vectors. I'll introduce them. We'll talk about their addition, so adding two vectors, the scalar multiplication of vectors, position vectors, the norm, which is just the length of a vector, and the component form of a vector. So after that, we'll do some applications of them. There are applications in geometry, and then we'll do some physical applications like forces, displacement, velocity, momentum, etc. And then we'll talk about how the scalar product and the vector product can have applications as well. Okay, then we'll move on to complex numbers. Okay, so complex numbers. My friend Indy asked me to do a video on imaginary numbers, and I told her it was coming soon. So this is Indy, where I will explain what imaginary numbers are. So I'll introduce complex numbers and then talk about complex numbers in polar form, and we'll talk about the powers of complex numbers, so we'll be able to find powers and roots of them, and then we'll talk about the fundamental theorem of algebra. After that, we'll be in a good place to move on to functions, which I'll introduce, and then I'll go over a collection of standard functions that you are going to want to have a handle on because they crop up all the time. Talk about solving inequalities, the composition of functions, inverse functions, and here I'll probably talk about as well, so inverse functions don't always exist, so I'll also talk about cases where you can take a function for which an inverse does not exist and apply some appropriate restrictions on the domain of that function in order to guarantee the existence of an inverse. And then after that, we'll be ready to move on to limits of functions. After we've done limits of functions, that'll put us in a good position to start doing some introductory calculus. So we'll do some differential calculus. I'll talk about tangent lines, the derivative of a function, and we'll do some differentiation rules. So rules like the power rule, the product rule, the chain rule, the quotient rule, those kind of things. Some critical points and curve sketching, and then I'll talk about some of the applications of differentiation, and then after that we're in a good place to move on to integration, which is a bit like undoing differentiation, right? So if differentiation is like multiplication, then integration is kind of like division, okay? I'll talk about antiderivatives and indefinite integrals, the area under a curve, definite integrals, and the fundamental theorem of calculus. So the fundamental theorem of calculus, I won't prove it in this video series because it's beyond the scope of this video series, but that will definitely come sometime in the future. I will do a video series on real analysis or mathematical analysis, and probably at the end of that video series I will prove the fundamental theorem of calculus for you. Okay, so just since I mentioned it, analysis is the branch of mathematics that evolved from calculus and basically made calculus rigorous. Okay, so analysis is the language for basically proving that the mathematical objects that we study in calculus actually exist in some sense, and all of the theorems and claims we're making in calculus are on firm epistemological ground, so to speak. Okay, so analysis is where we prove that calculus is not, okay, or that it's not nonsense. Anyways, moving on. After that, I'll talk about an integration technique called substitution, and then we will discuss some applications of integration. And then we'll move on to sequences and series. So I'll introduce arithmetic and geometric series and some applications such as to population growth. And then I'll talk about mathematical induction, okay? And mathematical induction is something that I will spend a bit of time on because I think it's often taught in a way that's a bit overcomplicated and confusing, and people often struggle with it when they see it for the first time. So it actually doesn't help that it's poorly named, okay? So mathematical induction, if you've heard of induction in philosophy and in the scientific method, so if you've heard about inductive reasoning in those contexts, this is not the kind of induction that we mean when we talk about mathematical induction. In fact, there's nothing inductive about mathematical induction, okay? That's not just my opinion. Any mathematician will tell you that. Okay, so mathematical induction is actually not inductive at all. It's really a purely deductive process, which is the opposite of induction. Okay, and if you're a bit skeptical of what I'm saying, consider this, that mathematical induction is a proof technique. Okay, so it's a way of proving certain kinds of mathematical statements that meet the appropriate conditions for being able to apply mathematical induction. Okay, so given that it's a proof technique, right, inductive reasoning is a probabilistic, uncertain kind of reasoning. Okay, there's many different types of inductive reasoning, but they are all probabilistic kinds of reasoning. Okay, and inductive reasoning always carries a degree of uncertainty. Okay, and since mathematical induction is a proof technique, proofs don't carry any uncertainty. Okay, so that should be enough to suggest, I think, that mathematical induction is not really an inductive process. Certainly not the kind of induction that you may hear about in philosophy and science. Okay, it's often taught. Or it's often explained by referring to like an analogy. So you know, the analogy is a chain of dominoes falling. Okay, so if you know that the dominoes are arranged in a certain way, and you know that the first domino falls, then you know that the rest of the dominoes are going to fall. Okay, so I will also use this analogy as well. I'll also teach it the way it's usually taught, but then I'll teach it my own way as well, because even with the domino analogy, even though that analogy is simple, what's not necessarily simple and straightforward is seeing how that that analogy with the dominoes is actually analogous to mathematical induction. And I think the domino analogy is perhaps a bit more complicated than what's really going on anyways, okay? So anyways, moving on. This will bring us to the last topic, and that will be matrices. So I'll introduce them. So matrices, plural for matrix, okay? I'll talk about adding and subtracting them, the scalar multiplication of matrices, multiplying matrices, the transposition of a matrix, so the transpose of a matrix, identity and inverse matrices, the determinant of a square matrix, and actually I will give a brief mention here of what a determinant actually is geometrically, okay, because determinants are not just some number that you can calculate from a matrix, they actually have an important geometric interpretation which is often not mentioned in mathematics classes. They just say, hey, the determinant of a matrix is a number that you calculate this way. This is how you calculate it, and this is how you use it, and things like that. But often you don't really get told what a determinant actually is. Anyways, after that, I will talk about vector products, also known as cross products, okay? And then we'll talk about solving systems of linear equations using matrices. And I think that will really be enough. And I'll make another video series after this, and that will probably be on calculus and linear algebra, okay? So some background knowledge, then we'll do vectors, then we'll do their applications, then we'll do complex numbers, okay? Then functions, then differentiation, then integration, sequences and series, then matrices, okay? Oh, stay tuned. The next video to come is on set notation, I believe. Yes, set notation, real numbers, and interval notation. Okay, cool. Thank you. And I'm not going to say if you liked this video, blah, 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 because, you know, I'm just really telling you what the contents are going to be for this video series. But seriously, give it a like and subscribe.